Sorry for the delay. It's kind of usual with me, but I think we are on time, minus 1 minute. I'm going to cut short on the bullshit. So for the guys who don't know me, I'm actually working for Pivotal, and my name is Stephane Maldini. I work for the project Reactor as a lead. But to be honest, nowadays we are kind of multiple leads on the project, so it's not like I'm the lead itself with a big L. And I work on the Spring Framework 5 as well, which involves a lot of Reactor 2, so my contributions are welcome here. So today we're going to speak and to discuss maybe the advantage of using Reactor for anything reactive on the JVM, and specifically the Java 8 version, because we build on top of Java 8. Of course, every time we talk about reactive framework, we have to do this kind of micro slide about the 4 threads of reactive. So here's a TLDR version. Let's say reactive is used to define producer-consumer problems like event-driven systems. We have something called a reactive manifesto somewhere that defines the quality of a system, but don't explain how you implement really a reactive system. It just explains how it looks like, but it doesn't go further. Myself, I tried to read it like a few times, and I failed apparently understanding it. So there is a specific thing we're going to talk about with Reactor today, which is the reactive programming part. And reactive programming is really the action you have to take yourself to move from imperative blocking code to non-blocking. So that's where Reactor helps, because it gives you structures, it gives you types, every tool you need to move from imperative code to non-blocking. Specifically, what we try to address is not to solve performance matters or low latency stuff. That's a different maybe a side effect of moving to non-blocking, but not necessarily the end goal. We work for stabilization, and we work for a consistent and a robust system that is resilient to failures, for instance, but not necessarily to get it faster. So that's the common misconception about reactive, but this talk is not necessarily about reactive itself. We use Reactor to decorate any kind of access to I/O or any kind of negatively impacting in terms of time for the producing call. We decorate any kind of call that might take time with a Reactor structure or tool. So before getting further, it seems like reactive is all the rage right now again, specifically since the reactive stream stuff. The specification actually went out last year in April. It has gained popularity, traction, and maturity as well. But does that mean, like, because some tool is becoming mature, you have to change to use that tool now? Because it still applies to a certain limited use, broad range of use cases. The thing is, it's definitely not a free lunch if you move to reactive programming, and if you start using Reactor. I'm not going to say it's easy or it's easier to do it with Reactor. It's normally here to help you creating non-blocking code without some of the issues you might face, but not all of the issues. And still, it requires a mindset change. You don't receive things immediately when you call, for instance, find user. You won't receive a user. You will receive an indirection of a user, a promise of a user, or a stream of a user, maybe, or whatever things of a user, but you don't receive user. So, changing in a functional way, adding this level of direction is necessarily going to be costly and add to the readability of the code. So here's the reason why you might want to look at this stuff. In nowadays, microservices are all the rages, and our story, and basically why Pivotal is embracing reactive story as well, is because there is a strong connection between reactive tools and anything distributed. And of course, today we become more and more distributed by nature, because we have distributed architecture, like microservices architecture, but also we have different kind of clients as well consuming our data, like mobile, with different bandwidth, with different rate of consuming not going to be as fast as the next phone next to you, for instance. So really, really kind of new set of use cases exploding since a few years. And if you think about these use cases, they all introduce, you heard about that, latency. And more importantly, they introduce a kind of latency that is very hard to manage because, as I said, someone next to you with a 3G connection will be faster than you with your 2G connection, connecting to your REST service backend, maybe. And for a server container such as Tomcat, it's difficult to handle different processing, different consuming rate like that without being or compromising in efficiency. And that's why Tomcat has, a thread pool, for instance, a large thread pool. And with this large thread pool, it will do the request response onto the same thread assigned by Tomcat. And that's because some client will be slow, some processing logic will be slow, and some will be faster. But the problem with this kind of architecture is everything slow is going to impact all the rest. You don't have a disconnect between them. So you don't want to do that. You don't want to apply that, if you have a mobile consuming client. You don't want to apply this kind of architecture maybe for this kind of use case because you will necessarily have slow client in that case. So with the microservice architecture, we have the idea, the hope that when we scale application and load balancer can be exchanged by any kind of term like RabbitMQ or a message broker, for instance, or a gateway, but something that we route requests to applications or microservices. And we hope that when we scale this kind of thing, if application B is on demand, on peak load, we're going to just mutualize the host 1, physical host 1 and host 2 with the current application. So we're going to pull this host to use more of them and hope we can scale up even more. Sometimes we even collocate when you scale up. And elastically undeploy. When you don't have a need for them, you can free the resources. So that's the advertisement for microservice architecture with a really decoupled application architecture where you can deploy some set of functionalities separately, use your host efficiently. But the problem is, as usual, this application, and if you are a consultant, raise your hand, because if you're a consultant or even in production, you have met with this kind of issue. Can you predict the load of your application? Can you do a capacity model for your application? Which is kind of bullshit because we know we can't succeed in doing that except applying some very constrained rules like blocking onto a certain load after a certain threshold. We don't accept requests, we drop this kind of action. But we can make really a proper capacity model because most of the time we deal with messaging system or threading mechanism like the pool in Tomcat that has unbounded queues that can accept in an unbounded way messages can explode because there is no such thing as unbounded memory. At some point, if you don't set a limit in your queue, it's the JVM that's going to tell you that you're going a bit too much further, unless you are data grid and you use the JVM as a pool, a memory pool. But the problem is we can't predict really the load, and usually it ends up being we can predict the efficiency of an application and the capacity of an application, and usually it ends up consuming more than what we expected. And that is actually the problem, the main driver, because when you want to scale such applications that are, bottlenecks in themselves, and they can scale efficiently, like we've seen, multiple one pooling the same resources, you have to ask for a new resource, and we know that in most of the company and enterprise development, it's not only about money, because of course it's going to cost money to ask resources or more physical resources, but it's also about the time, because sometimes the time you provision a machine is going to take months, and you want to just reuse, the current physical machine you have. So the TLDR is, being more efficient with the resources you have, with mutualized resources, which is kind of cloud architecture, is really the driver for this and what we do right now. And that's where we're going then. The reactive streams and Reactive API are the two things we're going to look after to solve this issue at the programming level. You might look after something else for a system-wide solution, but at least for each individual JVM application, you're going to change progressively your way of coding if you have, again, the use case for it. So let's look at the two building blocks for this kind of thing. So reactive streams, the specification, if you haven't heard about it, it's a collaboration between few companies like TypeSafe now / Lightband, Netflix, Red Hat, Oracle, because this thing is also going to be in Java 9. It's called flow.publisher or flow.subscriber, so they have a flow prefix. But that's the same thing that the 4 interfaces exposed by reactive stream, except they have a different package name, which is going to be a pain for library maintainer like us to deal with. But we're going to deal with. So reactive stream is a cross-collaboration to at last define what means reactive. That's why I don't emphasize too much on the word reactive, because now we have a clear definition on the site. We agreed on that definition. It's not like a manifesto or whatever. It's like a real thing explained on a GitHub page. We have to implement with a TCK to test the rules. So reactive has a real technical meaning. Not to say scientist, because it's a bit too far in IT, but at least it's concrete. You have tests and stuff, and you can use it. And it really looks like it's just about the problem of decoupling the publisher-subscriber concern with the addition, because that kind of solution exists. It's an observer pattern. You can call multiple subscriber indefinitely without issue, or an event bus, for instance. You could notify a consumer without any kind of back pressure. You just call a notify method or something like that. But the specific thing reactive stream add is like this control, this volume control, which is the reverse flow from a subscriber to ask for more data. And that's precisely where we position ourselves, because apart from as a full stack library, there is Aka Stream, which implements that. But by the time when we started doing the reactive stream specification, we were already focusing on creating a streaming library focusing and based solely on reactive streams. So the Flux and Mono things are the spoiler alert, two main components of Reactor, and that's where we position ourselves. So the cool thing about having back pressure, because we call that back pressure, when subscriber can say, I don't want to receive more data, that's a form of back pressure in the sense that you're not going to block if it doesn't ask you for data. You're not going to force pushing to it. For instance, it's very practical for everything which has a queue. Usually when you have a queue, you just do, when you have something based on a queue, because if you have a queue, you can do offer and deal with the offer. But if you don't have a queue, if you have, for instance, an actor or an executor service, you're going to call the execute command with a renable. And what if it's full behind? What if the executor service itself is full capacity? You're going to block at some point. Or maybe you have an unbounded queue, and then it's another problem. You're going to block anyway, because you're going to go out of memory at some point if you have a constantly faster producing rate anyway. So why is that important to have this concept of back pressure? Well, if you wanted to not block at first, what would be interesting is in that specification is you can have a callback for when you have actually the right to call the executor. And if you implement this mechanism, this callback mechanism, can I write to you for the next 10, 20, or 2,000 elements, for instance? If you add this kind of mechanism, well, you don't have to block on the queue because you're not being asked at first to send data. And if you reason in terms of distributed system, with the full picture where you have microservice accessing data stores, another service through HTTP, for instance, or a message broker, what if you didn't access them at first because yourself as a service A, you're not ready? And why you will be not ready as a service A? Maybe because the connection coming from the customer or the client or whatever, the mobile clients coming from the left will be like slowing down or not ready to process the data. So why trying to aggressively prefetch data from the backend storage or services if your consumer in the end cannot consume them. So that's the idea of having a back pressure. If you can have a back pressure and you can propagate it end to end, you will be super happy, to have a end-to-end flow control, because you have what I said at first, a capacity model, which is important sometimes when you do mutualized resources. If you have a end-to-end flow control mechanism, you can say, okay, I know this thing, volume control, is not going to consume more than 200 events. So that's my prediction, actually, because you know how much an event might be weighing in terms of weight, like kilobytes. So you can multiply that by the number of accepted elements in your system for a given time. And the maximum in-flight data defines for you the maximum capacity of your application. And if you think your application can consume more, if you have a need for more aggressive prefetch, you can tune that button thanks to these interfaces. So that's the idea, with a flow control, everything, applies a form of back pressure through blocking, through callback, maybe with reactive streams. But if we had an end-to-end, back pressure, in the end, you will serve more the ready client, on the left, the mobile client, for instance, ready to accept the data, the fast one, the 4G ones, and smartly, in fact, naturally deprioritize the slow client, but at least you keep serving the fast one, and the slow client will be served at some point eventually, but you're still super available for the rest of your consuming base. So basically, even for a sample case for like a CRUD, you have a backend, just a database backend. You could use this kind of patterns to implement a non-blocking way to save on database and be super tolerant to a certain volume of requests, unlike a classic, thread per request pattern like Tomcat blocking mode, because there is a non-blocking mode, of course, in Tomcat as well. So technically, how it looks like, if you don't, if you come from imperative world, and you probably have this kind of code anyway, or you went through that at some point. The problem with this code is when you return flying user, you don't know, if you have to get a user, so you don't know how much time it's going to take, but the API took the decision for you to wait, and you can't do anything from that. You can execute, maybe you can wrap all of that into a different thread, but you're not solving the issue that this call itself is going to be blocking. Also, another problem we can face is, especially with data access, the problem is you can throw exceptions. And we talked about a few threats in reactive streams. One of them is to offer resiliency to consumers and publishers. And mainly, the publisher shouldn't be impacted by a failing subscriber. In that case, you don't really know, because it's going to throw an exception. You will have to catch the exception. It's going to impact your call in any case. You have to deal with that in the main thread. Which is not good, because if you fail that and it's a thread serving resources like HTTP thread, you don't want to fail it, basically. You want to isolate that to the downstream component. So how it looks like into reactive streams. In reactive streams, you will do the same thing, and your service, you will implement publisher instead of just user. It will return a publisher. So there are a few things about that. The first thing is implementing a publisher is not easy. So you will probably only for that reason decide on some library doing that for you at some point. But also, there is also the subscriber part you want to implement, which has been designed in Reactive Stream to be easy to implement compared to the publisher. We placed all the complexity of implementation in the publisher. The subscriber has 4 callbacks: on next, on error, on complete, and a start callback, which we call on subscribe. And these are relatively easy to implement. They are thread safe, because in Reactive Stream, one thread at a time can traverse a subscriber. So there are some rules. There are some rules like that we also have. But implementing that yourself is not going to be the easiest thing you want to do, especially with good weather like that. So now the change is user repository find user will return immediately because it's non-blocking. The logic, the hard work is factored in into the publisher, and whenever we subscribe, that's when the slow or hard work is going to happen. It's kind of deferred. So when you call just find user and that returns publisher, it's kind of immediate. It's not doing any access. The problem with the publisher itself also is you don't have a distinction between one publisher, a publisher of one, and a publisher of n. So you know that if you have an API, you have an API that returns a find user, an API that has a list, for instance. For the list, you will return list of user, and for the find user, you will just return user. But we don't have this distinction in reactive streams actually or currently. So there is a miss in terms of meaning and semantic. We don't know if we're going to receive one or many user, even if the find user is going to return one. It's a bit like, if you use publisher, it's a bit like typing all your API with iterable of user without distinction, even if it's only one. So that's another problem you might face if you just use plain publisher. And implementing the callback is not also, well, it's straightforward to a point if you know the rules, but sometimes you will prefer just to have a shortcut to that. So that's it about publisher. What does it offer apart from that? If you command space or control space on your IDE publisher, you end up having this subscribe method, and yeah, what do I do with that? I have a subscriber, that's cool, and that's it. You can do anything. You can add continuation or add operations to do things we have already implemented for you. It's just subscribe, and you have to implement whatever you wanted to implement yourself. And yeah, most of the time you don't. So we can have a look at the reactive now, the reactive APIs around. And a colleague of mine, Sebastian Deleuze, did an interesting comparison, comparing even the Java type with the reactive type and what we consider blocking, non-blocking, reactive streams. So, if you the blog post actually is there, so I will show you after the thing to navigate to it, the QR code. So once you get into reactive programming, you will face the question: how is that different from future, for instance, or how is that different from completable future? And what about stream? There is a stream stuff in Java 8, and you say you're based on Java 8. So what's the difference with stream? So the way we perceive things, at least, but I think it's a shared as well, is the blocking side. At least we agree that for blocking value, your method will return void. Without value, you have something that does processing and doesn't have to return a value. You will just return void, and that means inside it all the processing happen. It's not like deferred. For a single value, we of course return T, like the user earlier, but also we consider future as a blocking type. Of course, because it doesn't really solve the non-blocking thing. At some point, when you have a future, you have to get the value, and get is obviously blocking. So you don't want to. Future is like a real problem, and basically they redid all of that with completable future. It's basically the right future it should have been since the beginning, probably. But anyway, future.get is not the one you want to use if you want to do non-blocking code. Then you have multiple values, how to deal with things that return multiple values. So in a blocking type, you will use iterable or collection, for instance. But we also consider stream inside this category as well, interestingly. So stream has a parallel features as well. If you know about stream, there is something called .parallel. But from the creator itself, it hasn't been designed to deal with a thing that can generate data with latency. It's really designed to process, over collection. Especially, it's super efficient over primitive type. And also in Reactor or reactive stream commands, the project we depend on, we always benchmark ourselves against the stream because that's the fastest thing you can do in terms of composing this way. And for instance, we will say we're 2 times slower, and actually we're 40% slower in synchronous mode than a stream mode. So you see we are slower because we do have overhead because of the request lifecycle, the back pressure thing we have to take care of, even if we apply optimizations. But stream really is not designed to to protect a latency-driven service like a remote call, like a REST call, or this kind of thing. Then you have the non-blocking thing. The non-blocking, you can do that with the completable feature in the JVM. So you can use the completable feature void, for instance, to see signal completion in a non-blocking way. You don't have to get, you can just add a continuation through the then method. Same for the single value. And then the problem of completable feature comes with multiple values. How do you deal with multiple values in that case? Well, that doesn't work that well. You will have to return a list. So it's at some point that means you will have to block for aggregating that list, but not necessarily block the CPU, but block the processing time, the response time, or increase the latency. Then you have reactive streams, which I said as publisher void, publisher T, no distinction. And then there is Rx Java, which is famous for implementing the reactive extensions, and reactive streams is derived from Rx Java, or reactive extension in general. So in Rx, multiple types have been created over time, but at first they were like publisher, everything was observable. Then in 1013, they added the single type to deal with the semantic difference between a publisher of 1 and n, and then they added an explicit one for the specific observable void. If you have a publisher that doesn't emit data but just signal. And in Reactor, what we translate, how we translate that is we have a type called mono, which is used for at most 1 value, and a type of flux, which is used for at most unbounded value. So it can be 1, it can be 0, it can be n value, but that's the most generic type you can use. And that's how we, that's the kind of type you can map to in your head when you compare.
Sorry.
Yeah.
One question.
Yeah.
I don't see. Okay, I'm okay for the multiple values thing, but for what regards the single value, I don't see the difference between, for example, a completable future and a single of T or a mono of T, because you have a callback when that value is available. So and that's all, and you are done. It's not a flux. It's not a stream of data. So
when do you start the processing with a completable future? How do you know when it's starting and where it's starting actually? When you subscribe, when you add a continuation. So the question is, what's the difference between completable feature, for instance, and mono or single? Mono and single have a method called subscribe because they implement a publisher specification, and nothing starts before subscribe is called, and then nothing is sent to the subscriber before a request, because there is the back pressure mechanism also before a request of 1 or more comes to the source of the data. So you can tell you don't have this reverse flow on completable feature, and you can.
But normally, I believe you don't need back pressure for a single value.
That's true. That's very true. Except if the one value is very slow, and if you deal with parallelization in this kind of streams, you might have a scatter-gather kind of pattern, and you will do fork, you will use the single return. And maybe you wouldn't ask for this single to operate until the other in the backlog have been consumed. So you can have a kind of capacity-driven parallelization. So that might be a reason. I know it's not a decision, an unanimous decision. Oh, sorry. For instance, I've seen Lagom. They use a completable stage or completion stage for the single value most of the time. And maybe that's fine. Sometimes when you can find the right type on the JVM, it's better to actually use it, obviously. And that's also why we base ourselves in Reactor 2.5 on Java 8. We didn't want to introduce callbacks like Rx Java introduced callbacks. So we use the functional callbacks. But you're right, maybe there is a case for most of the time, and actually we can convert to and from completable future. But most of the time, maybe you don't necessarily need the back pressure for a single element, except if you want to orchestrate this, single.
Okay.
So in that case, yeah. We have a specific case, Cloud Foundry Java client. This kind of case, even if it's a single or mono in our case, the things they do behind might take time because it's like deploy an application. I mean, you don't want to. You want to have a certain control over that. You want to subscribe when you want. You want to maybe request when you want, because you don't want to do anything. You want to keep the control because it deploys real application behind. It takes time. You don't want to deploy more than 10 at a given time, for instance. This kind of thing you can do by orchestrating and requesting at a given time. But I invite you to have a look at the blog post from Sebastian. It's quite interesting. He comes from a perspective as well where he learned this kind of thing, from a pragmatic eye, how he perceives things. It's interesting to see. So we do have in the category Reactive API, Reactor, RxJava, AkaStream. So there are some research, and the guy from RxJava, we collaborate on Reactor now. David Carnock has made a kind of classification. I invite you also to read his blog. It's very interesting. And he classified into few generations, but that's not the most, distinctive trait you will find between libraries, probably. They all implement some kind of operations. You apply to a sequence of data, and you can consume in the end. And that's, the common thing. As long as they implement reactive streams, they can talk each other. RxJava 1, unfortunately, doesn't implement reactive stream, even if it's super close and the bridge is not that far away. But the design internally will need to change why they try to do what they try to do with RxJava 2 if they manage to do it. So 2.5 in Reactor looks like that right now. We are a cross collaboration between the Spring team, Spring engineering team, and a research project we have created, a bit like JC Tool. If you know JC Tool, we have created something called Reactive Stream Commons. It's something without the noise of a framework, just plain implementation of Reactive Stream Publisher. And you can be inspired, by the pattern, the logic, or the algorithm. We have used that because they don't suffer the noise of Mono and Flux and all the Reactor special features. So you can look at that, and that's where we experiment with a few things, actually. It's strongly inspired by Reactive extension, but directly applied to reactive streams. We have I/O stuff. We work with Nelly for now and Aaron. We're not as probably as stable as the 2.5 M4, which is currently staging. Hopefully, will release by the end of this talk. So, yeah, that's a bit why also I was late, sorry. But M4 is staging, and we'll see. And Spring, the collaboration is we don't depend, Reactor Core, the jar doesn't depend on Spring, but that's the opposite. Spring depends on Reactor Core. And that's quite, it's massively new for a thing like Spring. For 12 years plus, Spring never depended on any kind of jar. And now, for Spring 5, they will depend on one that will screw everything, Reactor Core. So, right, and to talk more about Reactor Core precisely, we need Java 8 because we use the Java 8 contract like Java util function. We also convert to stream and completable future. So we're heavily based on Java 8 as a contract. What we introduce mainly is two types, Flux and Mono, but they can be hard to read because it's a functional API, so there is a bunch of stuff you will have to read. We did some diagram to help, but we have a strong focus on efficiency. We are kind of using GMH, every day or every twice a day. But we do that, that's true. We do compare with other frameworks as well, like RxJava or AkaStream. And we recognize where we are faster. That's some reason explain things. For instance, for AkaStream, they can be slower, but they have a specific reason and the actor model behind to back that. For RxJava, the things are different. RxJava 1 is slow because compared to Reactor because the design is done for 1 to 1x basically, and they try to refactor this design to change for 2.0 plus. And we try to improve on things like debugging, logging. Obviously, we're not going to release a GA without strong support for like graphing whatever you have done with your flow, or sanitizer for exception. These kind of things are really important to us because otherwise we're going to lose our Spring audience as well. The one who wants to just migrate calmly and progressively to reactive, because Spring is going to support both the reactive and non-reactive model in Spring 5 at the same time to offer, the chance to transition. And we do have diagrams as well. If you're familiar with Rx, that's a marble diagram. All the Javadoc is like polluted with that. Same for Mono. And interestingly, we had the chance to revisit the Mono diagram. We made some improvement from the original marble diagram. There are a few, like sometimes we show the request and the back pressure applied by a specific operator, which you won't find necessarily in Reactive X IO, the best documentation on reactive extension. And since we heavily inspired by reactive extensions, you will find a lot of patterns if you need documentation. And then, if we go back to this initial example, the imperative versus reactor, we still have a find user, but this time it will return a mono. And then you have kind of, shortcut, like you can use Lambda for subscribe instead of implementing the subscriber yourself. The interesting fact, obviously, the difference is you can type the single publisher versus the end publisher, or the 0. And you can also, start with the callback like that. If you need, more classic example of scatter gather. Here is an example of scatter gather using instead of a completable feature, it will use a mono, and the mono is created from callable. And let's say the blocking stuff value return a callable. It's calling, for instance, REST template, blocking REST template. If you use this kind of thing, one of the defining traits of Reactor, for instance, versus Akka, is we're really agnostic on the execution model. That means we're not going to jump thread if you don't ask us to jump thread. And there are 2 operators specifically done for that, as in Rx, subscribe and publish. That things will help you switch thread on the producing side, and publish, which is not here, will switch thread on the produced side. So here, for instance, we're going to have red, white, blue as initial values, and flat map, which is a kind of fork join in this example. Flat map is going to take each of these value and transform each of these value in something that takes time. And what is something that takes time? A publisher. And how will you transform each of these value into a publisher? Well, there are a few generators like static factories in Mono or Flux. And Mono from callable will be useful if this value is used to trigger a REST call using REST template inside blocking stuff. So blocking stuff is going to be blocking the callable it generates at least. And then you can subscribe on to tell, OK, use this. We have a notion of scheduler, which is a super form of executor adapted for us for reactive stream and reactor stream as well. So we can ask for a specific scheduler and say, OK, every time pick one thread from this scheduler, and you will run in parallel the blocking stuff. And when it's ready, you merge that back. We have operation like collect, which collect is going to create on star the result. Result is a container, and result add is going to be called every time. So it's a by function where you have the initial state and you accumulate the state from the event merged back from flat map. And you accumulate the result, and maybe another interesting difference is collect is going to, we have this kind of conversion between Flux and Mono. Collect is accumulating until the end. So what is the result of something emitting one and accumulating it until the end. We will switch the type from flux to mono in that case to limit the number of operation you can read, because you can apply, for instance, you can't apply things like buffer or create or collect. In fact, you can apply collect twice. What does it mean? You know, if I did write collect twice in a row here, what would that mean? Nothing. And that's what happens if you return, like in RxJava, an observable instead of a single from anything that produces at most one result. So we switch type when we can to just limit and make the navigation easier when you type and autocomplete. You know, the mono also has interesting API, so you can delay things. For instance, there are some very promise-like API like OR. We try to limit ourselves because we want to keep a consistency in naming to avoid explosion of names and vocabulary. So that's the real hard work, actually. Naming is super hard in functional API because you can easily argue for a given name, but we try to limit ourselves in the API. So in that case, for instance, you will have the interesting use of the only blocking method we have, which is block for mono. Before it was called get. It just changed for the M4, actually. It was called get, a bit like future.get. But we exported the same problem as future get has. It seemed like, you know, super nice. You can do a get, and maybe it's cached behind or not. It's cool, but actually most of the time it's blocking. So we just change the get and just use block. So every time you try to use the mono and block for a value, you won't use get but block, and you will see that something is going to be blocked. At least you're going to block until the value is returned from block. And that's important. Otherwise, you easily miss it, and that's from experience. So I told about the Java doc we have. I talked about the efficiency, but really the best thing is not to show the diagram, because they all depend on the system, environment, etc. Just if you want really to challenge this stuff, you go on the GitHub, you download this stuff, and you run it, and then you make your own opinion. But no diagrams here. Why David calls Reactor a fourth generation reactive library is because we do implement something called operation fusion, which is a way to avoid the request overhead. So basically, we try to revert the fact that we have added back pressure with other means, which is interesting kind of catch-22 problem. But there are two categories of fusion we can apply. So for instance, if you type merge with, dot merge with, dot merge with, obviously, there is an obvious optimization we could apply here, like, okay, why if I just use one merge operation, because I did merge with 3 times? So that's the kind of thing we call macro fusion. It happens when you type, the operation chain. And when you subscribe, we have something called micro fusion, which is about avoiding creating queues. And that's also interesting because creating queues is costly, especially if you have, non-blocking operation. You can accumulate. Some of them have queues. So that means they create queue, that means they offer to this queue, that means they poll to this queue. All of this stuff add, overhead to your logic. With the microfusion stuff, what we try to do is sometimes we detect by pair if the parent has a queue, and instead of creating a queue as a child operation, we're going to use the buffer from the parent. So that's the kind of other short-circuiting we do to avoid, this kind of offer, poll dance we have to do in this kind of stuff. So that's really what we're trying to explore. It's a very hard topic. We're going to propose that as a PR for reactive streams to progress maybe on reactive stream 2.0 or 1.1. But that would be interesting to have some kind of optimization. It's hard because not everyone has the same way of optimizing flows, but finding a way to optimize things in a generic way will be very interesting. And then last, one of the latest additions in M4, for instance, the parallelization. Most of this stuff works well with flat map and windowing. That's operations dedicated to create subflux or delimited publisher. But that creates also a nested level. Remember, here, I did make the blocking stuff in parallel, That's cool, but that is at the cost of a nested level. I did have to use a flat map, and inside it, I created a different publisher, which I subscribe on, etc., and then merge back to collect. That's, this kind of fork join like that, in classic patterns will use this kind of writing. But with parallel, basically we remove this nested level. We just use an internal container. We have a specific method called run-on, but parallel free will be actually creating free sub-publisher, and you can apply some operation. There are even interesting way of coming back to a sequential or join back. So for instance, you could reduce, you could take the fastest or the most recent event if you don't want to take every result from every parallel rails. But basically, this thing will use 3 different routes. And because I created a scheduler that has 3 threads, basically all of them is going to be assigned to each of the parallel stuff. And the collect will happen in parallel. Right, and yeah. So to conclude, where we're going now, we have the Reactor I/O stuff we're working on heavily with Aaron and Neddy. Some experiment has started on Reactor Core JS to have that in TypeScript, so Flux and Mono, but in TypeScript. And we also started because David Carnock, is a researcher working with us, is a strong .NET developer from background. So we started, and he started basically all of the .NET port. So we will have this TypeScript, JavaScript, .NET, and I/O extensions coming with the 2.5. And most importantly, to conclude, the thing is we're going to be in Spring Framework 5.0 M1, which is going to be released by 24 or 25 of July, hopefully. And what does that mean, inside it? That means we need to add support for boot. We need to, and that started already. We need to add support for Spring Cloud. We need to add support for Spring Security. Handling security with this kind of pattern is a kind of interesting concern because, the callback are meant to be location transparent. So what about all this stuff using thread local in Spring Security? So that's the kind of thing we also readapt strongly to make it work with reactive flow. That would be great, actually. Spring integration. All the guys working with enterprise integration patterns up to now, why would they care about changing first? But then, how would you mix Reactor or reactive streams inside the context of Spring integration? We work on that as well. And Spring Data. So Spring Data has already started as well, for having repository, instead of returning iterable, it will return flux of user. This kind of thing, So the whole ecosystem of Spring is changing for Spring 5, meaning that the dream of having the end-to-end back pressure working is becoming closer to the reality than before. We can make everything. We can create a flux for everything. So we will need adoption from the ecosystem, and that's a great thing happening right now with Spring, basically. So yeah, that's basically it for Spring. I just wanted to mention about Spring 5 with this slide. We're not only going to support, for instance, Reactor. It's based on Reactor, but we have converter. And actually, Reactor itself, the core, the jar, has a converter to convert to RxJava and Java 9 publishers or subscribers. So you don't need an extra bridge. We do support the conversion between RxJava or self. And so for a Spring application, Spring is heavily based on inference on types. If you have an annotation and a type return, a method, a service method returning an observable instead of a flux, for instance, or accepting an observable instead of a flux or a publisher, even a simple value, we're all going to handle this. We're going to handle all these cases. We're going to convert transparently for you, so you can use RxJava as well. We're not, we're not thought terrorists, and we like actually our collaboration with RxJava as well. And the drastic change also happened at the. The drastic change also happens at the runtime level as well, because we need to support Servlet 3.1, but also now we support Neddy through RxNeddy or Reactor I/O, which supports itself Neddy as well. So we need this kind of bridge to runtime stuff. So now Spring 5 can support Tomcat as well as JD, as Neddy, as Undertow as well, which is supported too. And that's basically where we are. If one thing I learned about reactive streams in the end, I took time myself to really understand. I think I work on this stuff for probably a few years now, and every time I just feel like I all barely understood it up to this point. But there is one thing that helped me a lot in understanding all this stuff, and it's called Factorio, and I encourage you, if you don't know this game, it's on Steam. It's a great game, and if you want to understand more about distributed problem or concurrency problem, I think Factorio for you or for your kids is a very, very good game. I don't want to spoil it too much, so you have to try by yourself. I think it's £4 or something like that, but you need to play that game. It's like an indie game, so it's interesting and time-consuming. Anyway, if you have any questions right now, I know my time is up, but if you have any questions regarding timelines or reactive streams or what we do, etc. Any questions? Yep? No? No. No question? You. No question. Okay. Perfect.